Hello, my name is Zhao Jiaxi. I'm an undergraduate at Peking University and a major in mathematics. I'm applying for the mathematical PhD programs at Courant Institute, New York University. Today, I want to talk about some topics in my undergraduate research project called optimal transport. We first review some basic knowledge in this theory. Suppose we are given rho and mu two densities on the Euclidean space. We define distance called the Washington distance between them to be the infimum of x minus y to the square integrated with respect to pi xy. You can see this where pi is a coupling of rho and mu. We can refer this as a distance as a transportation cost between rho and mu. Optimal transport is now an active research area. It is intrinsically connected to the fluid dynamics, and some professors in Courant Institute, they are working using the tools from optimal transport like gradient flow to study problems in fluid dynamics. Also, optimal transport is related to the geometric analysis. P-Rieman's proof of Poincare conjecture use some results in this connection. On the other hand side, optimal transport also shows up in lots of application problems, like data science. We use linear programming to relate these two fields. There is a rapidly developing field called statistical optimal transport. They study the statistical theory based on optimal transport, and some professors and faculties in Courant Institute are working on this field. I sincerely hope to talk with them about these problems and gain better understanding. Last, optimal transport is related to the mean field theory, and this connection has already proved some results in machine learning and physics. For me, I think that Courant Institute has lots of professors who work on this field or use the tools and perspective in this field to tackle other mathematical problems. So I think that I hope to discuss with them and gain better understanding of these topics and try to use them to study math more generally. Now I like to prove a theorem in optimal transport. It's called contrariety duality. It gives a dual formulation of this optimal transport distance. We will write this distance here, and we introduce two parameters here called phi and the psi. You can think these two are two Lagrangian multipliers in here, and we just drop the condition that pi is a coupling between rho and mu, and we add a term here. You can see that if pi is not the coupling of rho and mu, then you can choose phi and psi to make this term arbitrarily big. Or if pi is a coupling of rho and mu, this term just vanish. So this first equality holds. And for the second inequalities, we just exchange this superior and infimum. This is a formal step. Yeah. And now we first take infimum with respect to pi, then take superior with respect to phi and psi. And we analyze this term concerned with pi, you can see it's an integration of this formula with respect to pi. And by the same philosophy, we find that this term can only be 0. And we get the last formula, where we only have this phi integrated with respect to rho and psi with respect to mu. And we require that phi and psi to be conjugate to each other. And this is the dual formulation of this optimal transport problems. And this contrariety has connected optimal transport to data science. It has already very beautiful results in here. So here is my introduction. Thank you.